Hello class, welcome to exercise 4A, trigonometric ratios, and welcome to a new block of learning. This will be your time to shine with trigonometry. In this lesson, we have two examples, and example 1 is solving for an unknown in the numerator. And your pre-learning for this is question 1 and 2 in the new book, and question 4 in the old book. And then we'll do example 2, solving for an unknown in the denominator. And your pre-learning for this is questions 3 in the new book and questions 5 in the old book. With all the geometry and measurement that we've already covered in this unit, this will now make trigonometry a lot easier for you. However, we're going to extend trigonometry a little bit at the end of this unit, and we're going to really extend it in another unit later this year. So make sure you work hard to master all the topics, even if it feels a little bit like revision to you. You also need to make sure that you've mastered similar triangles. And with that, I'll see you in the introduction. Trigonometry has been used for thousands of years. It's very important in finding distances, but more about this in our lessons on applications. Now, it may feel like trigonometry is just a maths function with the way we use the calculator buttons, etc. But really, the key to trigonometry is right angle triangles and similar triangles. So the definition of trigonometric functions are, if we have a right angle triangle, and of course this box signifies a right angle triangle, and an angle theta, then this side here is adjacent to theta, and this side is the opposite side to theta, and of course this side is always the hypotenuse, then the function sine of theta is equal to the opposite side length divided by the hypotenuse. And cos of theta, also called the cosine, is equal to the adjacent side length divided by the hypotenuse. And tan of theta is equal to the opposite side length divided by the adjacent side length. And the easiest way to remember this with this silly word called SOHCAHTOA. And that's because the SOH, the SO, stands for sine equals opposite over hypotenuse. And the CAH, C-A-H, stands for cos equals adjacent over hypotenuse. And no surprises for guessing that TOA stands for tan equals opposite over adjacent. Now, it doesn't really matter what the length of the hypotenuse or the other side lengths are. All it matters is the actual angle. Okay, so why are these functions always true for a particular theta, no matter what size the triangle is? Well, that's because of similar triangles. Alright, so let's draw one right angle triangle with the angle theta and the lengths A, B and C. And if we've got another right angle triangle with angle theta and sides X, Y and Z, so by the angle sum of triangles, this angle must be the same. In fact, it would have to be 90 degrees minus theta. So that means by AAA, the similar rule, these triangles are similar. And this implies that they've got the same ratio between corresponding sides. So looking back at this triangle, we can see that Y and B are the opposites, and Z and C are the hypotenuse, and X and A are the adjacent sides. So because of similarity, Y over Z has to equal B over C. And of course that's also the sine of theta. And X over Z will equal A over C, which is the cosine of theta, and Y over X will equal B over A, which is tan of theta. Here's some other fun facts. If we have a right angle triangle here with angle theta, of course this other angle has to be 90 minus theta. And let's name these sides X, Y and Z. So sine of theta equals Y over Z, and cos of theta will equal X over Z. But if we now consider the other angle, sine of 90 minus theta will equal X over Z. And cos of 90 over theta will equal Y over Z. And that's because Y is obviously adjacent to that other angle and X is the opposite angle. Now if we look at the answers to those trig functions, we can see that sine of theta and cos of 90 minus theta are both Y on Z. So that means that sine of theta equals cos of 90 minus theta. And looking at the green cos and the pink sine, we can also see that cos of theta is equal to sine of 90 minus theta. So there's that strong relationship there. Now it's also worth pointing out that tan of theta is going to equal opposite over adjacent, i.e. x over y, And if we now consider sine of theta divided by cos of theta, looking at the values of cos and y of theta, that means we've got y on z divided by x on z. And simplifying that, that actually equals y on x. Whoops, I made a mistake. Earlier on, I said tan was equal to x on y, but actually it's equal to opposite divided by adjacent. So that should be y on x. And that leads us to the point that sine on theta divided by cos on theta is actually equal to tan of theta. And these will all become very useful in the future for you. Now it's also worth pointing out now that while sine, cos and tan are simple ratios here around a triangle, if you do know the angle but not the side length, you're still going to have to use a calculator. And that's because most mathematicians only know the exact answer for just a few angles. So I could use OneNote. Now you can type it in, or if you're lucky enough to have a fancy laptop, you could write it in. Now let's pick on sine of 38, because that's a difficult angle. You could also use something like the green calculator. And here you can see the sine button there. So let's just type in sine of 38, and that's 0.6. I got 0.2 here. I wonder why. Let's try and type it in. Maybe I missed something in the evaluation there. Okay, I'm not sure why I got the 0.2. I have to go back and check the tape later. Some of you may have a CAS calculator. And here you can see we've got this special trig button. And that brings up all the trigonometric functions. So just select sine, type in your number, close brackets and press enter. Oh, that doesn't help us at all, does it? So the trick is you can now press Control Enter, and that estimates it for us, because this answer is actually a long irrational number. So there you go, you must use your calculator for those sorts of angles. Now today's lesson is going to be about finding side lengths we know with the angle. So make sure that you're comfortable with your calculators. Alright, that's the end of the introduction. I'll see you in the next section. For a right angle triangle with angle theta, and we'll mark in the side lengths with the one that's adjacent and opposite to the theta plus hypotenuse. Because sine of theta is equal to the opposite side length divided by the length of the hypotenuse, if I know what the length of the hypotenuse is and what the angle theta is, then h times sine of theta equals the opposite length. And in this way, we can solve for the length of the opposite side. Similarly, cos of theta is equal to adjacent divided by hypotenuse. And if we know what h and theta is still, we can say that h times cos of theta equals adjacent. And with tan of theta equal to opposite over adjacent, the length of the adjacent times tan of theta equals the opposite length. Now this is the simplest type of trig problem, so let's not waste any time and get stuck into example 1. So in part A, we have a right angle triangle, and we've got this angle 27, and the hypotenuse is 11 centimeters. So in this question, we're asked to solve for x. Here we know that 11 centimeters represents the hypotenuse, and x is adjacent to that angle. So with hypotenuse and adjacent, we use ka, as in cos of 27 is equal to adjacent over hypotenuse. So multiplying both sides by 11, we now get 11 times cos of 27 equals x, ignoring the centimeters for now. So if we pop that in the calculator, we can see the answer there, and if we round that off to 2 decimal places, we get x is equal to 9.80. Alright, nice and easy. Let's move on to part B, where we have a right angle triangle that has one angle that's 69 degrees. And this side length next to the angle is 38 millimeters. And we'll call this other side length here x, and we'll solve for x. Now x is clearly the opposite, and 38 millimeters is the adjacent. Now because we've got opposite and adjacent here, from SOHCAHTOA we use TOA. So that means that tan of 69 is equal to the opposite, which is x, over 38. And multiplying both sides by 38, we end up with 38 times tan of 69 equals x. Once again, this is a calculator problem. And rounding that off for 2 decimal places, we get x is equal to 98.99. Alright, so that is pretty straightforward, and I'm sure you all did stuff like this last year. So right now you should pause the video and do questions 1 and 2 in the new and question 4 in the old book. All right, and I'll see you in the next section. This is a very similar process to the last section, all right? Now, because sine of theta is equal to opposite over hypotenuse, if we know what the opposite side and the angle theta is, then we can manipulate slightly differently to try and figure out h. So first thing we're going to do is divide both sides by the opposite, and that will give us sine over the opposite equals 1 over h. And you can flip both sides of the equation. So in the end, we end up with h equals opposite over sine. And using the exact same process, because cos of theta equals the adjacent over hypotenuse, then h equals adjacent over cos. And with tan equal to opposite over adjacent, then the adjacent is equal to opposite over tan. So this is just like the last section, except that we're solving for the other side and end up with our trig function as a denominator. All right, let's put this into action with example 2. And in part A, we have a right angle triangle that has an angle of 33 degrees. And this other side here is 21 meters. And we're going to figure out how long this hypotenuse is. So 21 is the opposite. X is the hypotenuse. So therefore we use SO from SOHCAHTOA. And we end up with sine of 33 is equal to 21 divided by x, because 21 is the opposite and x is the hypotenuse. And we can just jump straight to using the formula we already figured out. So that makes x equal to 21 divided by sine of 33. And this is definitely a calculator problem. So if you squint, you might be able to see, but rounding that off to 2 decimal places, we're left with x is equal to 38.56. Oh, I should say meters. All right, let's move on to part B, where we have a right angle triangle and an angle of 53 degrees. And this side here is 71.3 centimeters. And we're going to try and figure out what x is. So for this angle here, x is the adjacent and 71.3 is opposite. So therefore we have TOA. In other words, tan of 53 is equal to 71.3 over x. And using our formula, that means x is equal to 71.3 divided by tan of 53. And this is definitely a calculator job. And so rounding off to 2 decimal places, we get 53.73. All right, so this method is slightly more complicated than the last, but just remember SOHCAHTOA and the formula. All right, so you should pause the video now and work on question 3 in the new book and question 5 in the old book. And I'll see you in the next section. All right, so this lesson is mostly revision. Of course, the takeaway lesson is do not forget SOHCAHTOA. It's obviously the best way to remember your trigonometric functions. And for those of you who want to later on, you can check out this amazing song. Okay, so let's remember sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. All right, so in this lesson, a successful student will understand how the trigonometric ratios relate the angles and the side lengths of a right angle triangle. Know all the trigonometric ratios involving sine, cosine, and tangent. Be able to identify which trigonometric ratio to apply based on the information in a given right angle triangle. And be able to use trigonometry to find the unknown side length in a right angle triangle. All right, so they're all the things you need to know in this lesson. So it's a nice and simple start to this block. The next exercise will probably be just as simple for you. So we'll see you in that lesson. Have a good day. Bye.